hopefully everybody has this textbook, this book that we're going to be using. Um, that's the one we're going to be using to read from. And yes, sir.
Moving forward, how do you plan to divide? Like some lessons have been categorized for like 2 weeks. So how do you plan to like
Yeah. Yeah,
divide?
this is a good point. I haven't really thought things all the way through, right? I mean, because when I first started, I didn't anticipate that we were gonna. I didn't have the idea that we were gonna meet twice a week. So now things are a little bit up in the air. We'll have to figure out how those two meetings are gonna go. I mean, I think there's room for a lot more presenters if they want to. I know some people asked to present and you know, it was already taken. Everything was all the slots were already taken. But I think there's room now for people to sign up to help out with leading the discussions and so on. So I'll try to redo the schedule a little bit more. I did at least today start putting in the Wednesday meetings. But is that what you were asking about, Rekil?
Yeah, that was one thing. And like, for example, classification is divided into two parts, right? So where
Yes.
like if it's 40 pages.
Yeah, I see. I see what you're saying. Yeah. So I should probably think ahead of time, and actually I should let the
The
person who's
presenters probably
leading,
just,
yeah,
yeah.
the person who's leading that section should look over the material beforehand and decide how to divide it up in two. I just have this general idea that 25 pages is a little, if it's more than 25 pages, that's a little too much to read in one night. So anything that's what I tried to do, is to break things down into pages that cover 25 pages or less.
The hard part is you'd
Yeah.
cover 25 pages, but the following Sunday you would have to do the assignment or look through the course notebooks, and you should have probably covered that already in your reading for that to make sense.
Yeah. Let's see. I think, okay, so in the the 2 week chapters, we're going to have actually 4 sessions, right?
Right.
So we can go through half the material roughly, and then we can go through some of, maybe half. We can get partially through the notebook, the notebook that corresponds to that chapter, right? So,
Mhm.
and we have actually 4 sessions to get all the way through, right?
Yeah.
2 sessions for the notebook and exercises, and 2 sessions for the reading.
Right. Okay.
Yeah. Okay. Other questions before we get started?
Joseph, so I'm leading the classification chapter, I believe, and so I guess I'll probably look through the chapter and let you know if I want to kind of break into perhaps more sessions.
Yeah, I think I recognize your voice, Wenching.
Yes.
Wenchang? Sorry, yes.
Yeah.
Okay, so yeah, that's fine. Anybody that wants to, if you want advice from me on how to break it up, I'd be glad to have a look at it for you. Or I'll be glad to have a look at how you suggested if you're not confident of it, that's fine.
Okay, I'll let you know. Thank you.
Okay, sounds fine. Anything else? All right, we now have 1, 2, 3, 4, 5, 6, 7 times 4. We have 30 people here, so this is terrific. Thank you all for showing up. Let's go ahead and start reading, and let me see. We'll read for an hour, and then we'll reconvene at 7:40, and then we'll discuss till 8:30. Wait, is that what I want? No, I want to give you an hour and a half to read, right? So we'll do 7. Let's see, an hour is so it's 7:10, right? 7:10. Let's read till 7, and then we'll discuss till. No, sorry, I'm sorry. Let's read until 7:45, 7:45, and then we'll have a 45-minute discussion. Okay? On your mark, get set, go.
Did we decide to actually do the silent reading till 7 or 7:30?
7:30 it says. 7:45. Sorry, 7:45.
Thank you. Thank you.
Yes, yes. Okay, we're at the end of our reading, and hopefully you got your teeth into a good portion of that material. You may not have finished it all. Don't worry about that. You could catch up later, but now we should discuss what we read. So the first thing that I'd like to do is just get the conversation started by inviting those of you who wrote down some questions during their reading to go ahead and ask and see if we can get the community to answer your questions.
Okay, I guess a general terminology question. The difference between generalization versus regularization.
Yeah, does anybody want to handle that?
Yeah, I can answer. I'm not sure about the context. Some of these questions, I mean, having a context for some of these questions really helps in ML, if I'm not wrong. So regularization, whenever the model becomes overfitted, right? It's a way of actually penalizing a model. It's called regularization. Just a second. Hi, am I audible?
Yeah.
Right. So generalization, when you want your learned algorithm to be equally good on the unseen data sets, we typically say that the algorithm is generalizing well. There's no bias that the model is picking up from the training piece.
Yeah. So then, basically summarizing, it's so regularization is a specific technique that we'll use later on. We'll learn about and use later on to combat the problem of overfitting the data. And what is overfitting? Overfitting itself means that you are. I'm going to define this in terms of the other term you asked about. Overfitting the data means that you have a good fit on the training set, but poor fit on the test set, and that means that you're not generalizing well. Generalization means the ability of your model to handle new unseen data.
So then regularization can be termed as means to the end, which is generalization.
Which is good generalization. Yeah,
Okay.
exactly. Yeah. So, but hold on, and we'll learn about generalization. I'm sorry, we'll learn about regularization in a later lesson. I was surprised he mentioned it here without really defining it. I think that was usually you don't mention a term without defining it first, but in the book. So, okay. Other question.
Hi, this is Arushi.
Yeah.
Can somebody discuss about instance-based versus model-based models?
Yeah. Does somebody want to say something about that?
So yeah, an instance-based, we typically don't. What we typically do as example for instance-based learning is k-nearest neighbors. So what we're going to do is like every time we want to classify a point, what we're going to do is like we'll calculate some sort of a heuristic with the existing data. So typically the model learning does not happen upfront in instant-based learning. Whereas in model-based algorithm, you train a machine learning algorithm like decision tree, linear regression, or logistic regression. So you are deriving a formula y is equals to f of x. In model-based learning, you're essentially deriving that f. Whereas in instance-based learning, you don't derive that f. Rather than you want to figure out like how closely the point to the given data is.
Yeah, so another way of saying that is instance-based learning is when you have you've memorized all the data, you have some kind of a lookup table, and then if you're given a new piece of data, you just sort of compare it with everything else in your data and pick out the label, the label that most closely matches that particular instance. An example would be if everybody's familiar with this MNIST digit classification problem, right? Where you have something like, what is it, 32, is it 32 by 32? No, it's, I forget what the size of these little small images of digits, and you're supposed to classify the digit as whether it's a 0 or anything between 0 and 9. So one way to do this is you could basically have the data be a 32 square. I think is it 36 by 36? Does somebody know? No.
32, if I'm not wrong. 32 by 32.
Yeah, I think it's
28 by 28.
28. That's right. So it's 28 by 28 squared, which is 728. So you can map each image into a 728 dimensional vector. And then if you have an instance-based model, you can just basically memorize all of those 728 dimensional vectors and store them in a big lookup table. And then a new digit, a new 28 by 28 image, you just convert it into the 728 dimensional vector, and then go into your lookup table and find the one that's closest to it and say, oh, that must be an 8, or that must be. Do you see what the difference is between that and a model-based?
Yes, I get that now. Yeah, that's clear. Yeah,
okay,
thank
great.
you.
Yeah. Other questions? Okay.
Question about
yes.
the types of models here, major types: supervised, unsupervised, semi-supervised, and reinforcement. And I'm curious where the GAN would fit in to that. Is that something separate, or is that?
Yeah, I was surprised he didn't mention that. I'm going to learn about GANs when you do, because I don't know much about them now. But can someone say anything about how GANs fit into that hierarchy of supervised, unsupervised, semi-supervised, and reinforcement learning?
So I'm only just guessing here, but I would classify GANs more as maybe semi-supervised, plus online learning maybe, because what we have is like we have some known images, then GANs generate images based on the training set, and then learn based on that. So that's online learning there. And because only some of the training set is actually initially labeled, so that's why it's semi-supervised. So that's the take that I would take.
Yeah, so a GAN has two pieces to it. It has a generator and a discriminant. And so you might be saying, okay, I want images that are, I want images of squirrels. I want you to generate images of squirrels. And so then it has a generator that tries to generate an image of a squirrel, and then the discriminant looks at it and says, no, that's not very good, and it gives it some kind of a score. And so then the generator goes back and tries again, and hopefully gets a higher score, and then it slowly starts to learn how to generate a proper image of a squirrel. But in order to do this, you have to have labels. You have to have images that are known to be images of squirrels. So in that sense, it's got some component of supervised learning, and the interplay between the generator and the discriminant is some kind of unsupervised learning.
So, I mean, if you look at Wikipedia, right, the initial GANs were like completely unsupervised, but over a period of time, they've proven useful for both semi-supervised and fully supervised learnings as well.
Mm-hmm. So if it was unsupervised, then how can the discriminant say that, no, this isn't a good result?
So I think, I mean, the outputs of the both discriminator and generator will be compared, as far as I understand how it works. Maybe I need to dig deeper into it.
Yeah. But you might be right. I don't know enough about it to say whether it's right or wrong. So anyway, so that's something we will encounter later on. I think one of the later chapters in the book covers GANs, so we will get that.
Awesome. Thank you.
Other questions that have occurred to people as they were reading? If not, we could try to move on to the 19.
So one more question. Yeah, it's kind of more philosophical, but the very first few examples, or even almost all of the example applications stated, kind of almost all dealt with deep learning. So I was wondering where exactly like pure machine learning is useful.
Well, pure machine learning it came up in the context of tabular data, right? If you have sort of the data that you would encounter in an Excel spreadsheet, right, where the rows are the different training examples and the columns are the features, right? So you have a two-dimensional data table that you can, that you can think of as an Excel spreadsheet. And then if you have a label for each row, then you can try to build a model that takes in the features and build some kind of a functional representation of the features and maps them to a prediction of what the label should be. So yeah, that's the sort of the classic example is tabular data. Like the example he did here, he ran through in this first chapter where he was comparing a gross national product of a country to its life satisfaction index. So in that you would have rows, and each row would be a country, and then the columns would be, in this case, there's only one column, and that's a gross national product. That's the only feature that's going into your model, and then you have to predict the life satisfaction. So yeah, that's an example of a two-dimensional table, although it's more like a one-dimensional table because well, it is 2 dimensions, but it has a very skinny second dimension because there's just one column. Yeah, so the techniques that you've heard about, the random forest and the tree-based methods, let's see, there's random forest, there's SV, let's see, what's it called? SVM, yeah, support vector machines. These are classical techniques that you can use to deal with tabular data. And then, of course, there's the more recent, more modern versions of the tree models, the gradient boosting machines, where they seem to be really, really good at handling tabular data. And then more recently, they've discovered that, yeah, even though machine learning is, even though deep learning has been historically applied to images and to text, but there's a way to actually apply it to tabular data too, and it's sometimes competitive with even the best of the tree-based methods. It can even compete sometimes with gradient boosted machines. Yeah, does that answer your question about the machine learning? Where does machine learning, classical machine learning, come up?
Yeah, kind of. I mean, it's just a general trend of the field with deep learning kind of taking over more. I was just wondering more in terms of actual practical applications as to see whether machine learning can actually help some of my deep learning.
Oh, I see. Yeah. Well, in the course that we took.
Sorry,
go ahead.
I mean, Joseph, if you're fine, I'll probably answer that.
No, go ahead, Prasad.
Yeah, thanks. So I actually work as a data science manager for the past 5-6 years, and one of the areas actively researching is, I mean, when I say researching, I work for an applied data science team, not a pure research play. So to answer your question, for example, I used to work for a company called American Express. So the question that we want to understand is like, what would be the probability that a person would repay us at the end of their card due date, right? So in that case, we were using both ways. We were using creating feature spaces, machine learning, and feeding it with deep learning, and we were using the other way as well. So in tabular data sets, using creation of features using deep learning proved to be more successful than creating features just ML. So my understanding of deep learning is deep learning helps in actually creating the features rather than, I mean, ideally we need to do the feature engineering by hand in traditional ML, but deep learning helps us automate that piece. So
yes.
Yeah.
Yeah, and a big part of classical machine learning is feature engineering, and as you said, and this a lot of times requires domain expertise. You have to know what you're doing. You have to understand this field. So, for example, if you were working in this credit problem, you would have to know something about this problem so that you could create features out of all the pieces of data. Because I presume, I'm sure that, I mean, I don't know how this problem goes, but I'm sure that Prasad starts with bits of information about each customer, like their salary and whether they own a home or not, or how successful or how often they have paid off previous debts, that kind of thing. These are like the features that you get, and then by figuring out suitable combinations of those features, you can even get more powerfully predictive features. and as Prasad said, when you use deep learning, you don't have to know that stuff. The network will learn the right combinations of the features and so on. But as I was going to say, that if you've gone through the Deep Learning course 1 version 4 that Jeremy just had, in one of the lessons, I think it was the 7th lesson, he went into this. He showed how to use deep learning to do a tabular data problem. And then he suggested that in some cases you can make a hybrid model that uses the deep learning part to create the features, and then feed those features into a random forest model, and then you even get better performance sometimes. So that's kind of interesting too.
Okay. Is there an example, if somebody knows, of the other way around? I mean, here we heard how deep learning can help enhance ML. Can ML help enhance DL?
Well, I just gave you an example of how that could work. Because, in other words, you're building a model, you use the deep learning to generate the features, and then you feed that into a learning model, the random forest, and then you get a better result. So there may be other examples if anyone knows of any. Okay, well, this has been a really interesting discussion so far. Let's see, so now let's start looking at some of those 19 problems at the end. Some of these are pretty easy, other ones might require, but they're all in the book, so you can actually dig out the answers to any one of them.
Joseph, Subhashish here. Just one, two question. I missed the first part of this discussion. I was cut off from the meeting. So just 2-3 quick questions from me. Can I pose them now or after the?
Absolutely. No, you can pose them now.
Okay. So what is I didn't understand the difference between instance-based learning and the model-based learning.
Okay, so what we said was the instance-based learning, or this is my understanding at least, in a model-based learning, you take all your examples and you build a model. Maybe it's it could, if it's a regression problem, maybe you're going to build a quadratic model or something like that, or a cubic model, and then you have a formula. And if you have a new data point, you just apply the formula. If you have a new data point, x1, x2, x3, blah blah blah, you just apply the formula. And apply your quadratic or cubic model or whatever, and then you get an answer, right? So that's model-based. You come up with a model in a regression problem. Let's say you come up with a model which is basically just an equation, and you don't feed your data into your new data into the equation, and it gives you the answer. Okay, but in an instance-based model, instead of building a model, sort of in an instance-based, I don't know what you'd call it, maybe it's called a model, but you do something more like memorizing all your data, and then if you're given an instance, you just if you're given a new data point, which we call an instance, that's what they mean by instance, it's a new data point. You then go into your lookup table and find the data point that's nearest to that one, and then you estimate your answer like that. Does that make sense?
So as I understand, it is like in the model-based learning, we are looking holistically at the whole data set and coming up with a balanced model. But in the case of instance-based learning, we are just looking up the table, finding out the nearest data point and predicting accordingly.
Yeah, that's my understanding of it. Yeah.
Okay, that makes sense. The second question I have is, so I read through how to build the model and then apply regularization. So is it something like that during the ML process, we first go through trial and error process for several models, then we first zero in on a particular model after we have decided that this is the model we are going to use. After that, we apply regularization on that particular model. Is that the way it works?
You might apply regularization at the same time as you do your model selection. So this brings us to one of the questions in our 19 questions where they were asking about what's the use of a validation data set. And the question that you have is a really good one, because that brings us right to that question. So what is a validation set for? It's, in other words, why can't you just use the training set and then build your model and then go apply it on the test set?
Right.
Or why can't you use the test set to then go and select which model is better, or tune the model and then apply it? And so, the validation set is kind of like a data set that's in the middle between the training set and the test set. And the validation set is kind of like, the way I think of it is kind of like a playground to test out your models. It'll help you to pick out which model is best, and then it also helps you to pick out which regularization parameter. In other words, remember that regularization is a process that helps you to generalize better, but it's characterized by a hyperparameter, something called a hyperparameter. And you have to tune that hyperparameter to find the best value that will give you your best result. So you're going to use the validation set to tune your hyperparameters on the one hand and to select the best model on the other hand. And then once you're done with that process, now you build the model all over again with all the training data and all the validation set combined together. And that's your final model. You build your final model based on both of those. And then you apply your final model to the test set, and it will give you it will tell you how well your model generalizes. The thing you always have to be careful for is that the test set must be absolutely pure. It must never, there has to be a firewall between the test set and the validation set and the training set. If you do anything with the test data that influences your model, that's called data snooping, and it's bad, and it will give you bad generalization error. In other words, your model will look really good when you apply it on the training data, but then when you apply it to new data, it'll fail miserably. So always think of the test data set that has to be kept pure. The model can never see it, at all. Okay.
Okay, so as I understood, first we take the whole data set corpus. From there, we create three sets of sub data or subsets of data. One is the training set, the test set, and the validation set. First, we create the model using training set. Then we test that on the test set. Depending on the result of the test set, we zero in on a particular model that this is, let's say, the decision tree that we are going to use. After that, to decide which version of the decision tree will be best for me, that's why we apply regularization, and that regularization we test on the validation set. After all these things are done, we again come up with the best version of the model and apply that.
No,
is that a fair understanding?
Yeah, somebody wants to talk to that. Yeah.
Sure. So typically, whatever you're actually doing with respect to the model, right? You should not be using the validation data set or the test data set. I mean, whatever the data set that you want to evaluate your final model on should not be used for tuning your model. Regularization is sort of tuning as well. So the philosophy behind having an untouched data set, I mean, oftentimes people call it as test or validation. So I don't want to go into that debate of nomenclature. So the philosophy behind that, having an untouched data set, is whenever the model actually looks at such kind of a data set, there's a data leakage that happens, and the model try to learn some of the information basis the data set, and that's how it builds the parameters. So that's my opinion about it.
Yes, that's correct. Yeah. So I think what you said, the general Subhash, so when you were saying, you first said you train the model and then you try it out on the test set. And I'm not sure if you misspoke. I'm not sure if you misspoke. Did you really mean try it out on the test set as the first step?
Not try out. So what I try to do is that first, using the training set, we will train the model. After that, we will test the model. Let's say there are 10 models. We come up with that. These are the 10 sample models I want to test. So I will test each one of them on the test set. After that, depending on the test result, I will zero in on a particular model.
That's what I thought. That's what I thought you said. Right. So where you went wrong is that you don't use the test set at all. You don't get to look at your data and evaluate it with the test set. You don't get to evaluate your models on the test set until you have a final model. You understand? Because anytime you show your data to the test set, then that leaks, as Prasad said, that leaks into your model. Now your model knows something about the test data, so it's basically cheating. It's kind of trying to group itself and make itself so that it'll do well on the test set. So that's cheating. You cannot show the model the test set. So that's the test set is the very last step. Once you've built your final model, you're done tuning the hyperparameters, you're done picking the right model, you're done tweaking all the parameters in the random forest or whatever. all decided on your model, then you lump together the validation set and the training set, and you make your final model. Why? Because that gives you the most possible data points, right? The validation set and the training set together. The more data you have, the better your model is going to be.
Right. Right.
And then you try it on. After you're done, now you try the test set, and that tells you whether you did a good job or not.
Okay.
I have a question.
Sure.
So, like, I'm trying to wrap my head around when to use, when to split the data into training, validation, and test sets.
Yes.
Like, when do we need to do, like, normally when I do ML models, I usually do train and test.
Yeah.
But when do we do train, validation, and test?
Well, that's if you want to do if you're doing a really deep job there, you're trying to do this as well as you can, you have a lot of time to spend, your boss says do the best job you can do, then you want to do two things. You want to tune the hyperparameters and find the absolute best values. That's the first job. And the second job is to select the best model. If you have several, your boss said, throw all the models that you can think of at this problem and pick the best one. So that's where the validation set comes in. It's like a sandbox where you play and you test the performance and you find the best model with the best hyperparameters. Does that make sense?
Oh, okay. So you're saying before showing the model to the test set, you can keep on showing it to the validation set until you get the best.
Keep improving it and getting the best model you can get. And the test set never sees the model. It's only used for inference. You predict on the test set, and you see if and so you see how accurate your prediction was.
Okay. That clarifies my question as well. So basically, Stephen, first we first we prepare the model on the training set, then we expose it to the validation set for the hyperparameter tuning. After we are satisfied that everything is fine, then only we expose it to the testing set.
Exactly. The test set, the model never sees the test set, and the validation set is kind of like a playground where you can tune do the two jobs that you can do are tuning the hyperparameters and selecting among the different models that you have. And by that I mean like random forest, logistic regression, gradient boosted trees, supported vector machines. You might have a whole battery of models that you want to throw at it, and you want to figure out which is the best model for this problem. That's what you use the validation set for.
Okay, understood. That's clear.
Yeah.
Thanks.
Yeah, go ahead.
One question. Sorry.
Sure.
Can I ask my question? Sorry.
Sure, Alex.
Prasad here, sorry. So
sorry.
one question that actually hit my mind I never thought of. So the whole debate about test, training, and validation set, typically people speak in the context of only supervised machine learning. I'm just curious to understand if somebody had a similar approach in unsupervised setting as well. So as far as my exposure is concerned, I never dealt with test set in unsupervised machine learning.
Oh, that's a really good question. I think the philosophy is, let me just think through this thing while I'm talking. I think the philosophy is the same. For example, if you're doing k-means, if you're doing clustering and you want to do k-means, that means finding k different clusters. So you have this data in a high dimensional space, and you want to see how it clusters together. So you have to decide, like, do I want to find 3 clusters, or do I want to find 4 clusters, or do I want to find 5 clusters? Which is the best way to do that? And so you can then go ahead and do that and visualize how the data looks, and then see which number of clusters looks the best. Does 3 clusters look like it really does a good job separating the data, or does 4, or does 5? Which is the best? And so I think you would use your validation set. Again, it's kind of like a model selection. What number of clusters? That's the hyperparameter there, is the number of clusters that I'm looking for. And so you would do that using the validation set. And then once you're done, then you'd say, okay, I've made up my mind. I'm only going to look for 4 clusters. Now I get to try it out on my test data, and you can immediately see whether you did a good job. Because If it really separates the data into 4 clean clusters, then you've done a good job. But if there's other stuff cropping up elsewhere, then that may not have been the best model.
Yeah, makes sense. Makes sense. But I mean, one of the paradigm shift in the way of how model, at least iTunes, is like, I mean, we typically follow K4 cross validation approach, where you divide the data into 2 pieces, train and test. The validation automatically sort of happens in the fold training itself.
In the k-fold validation?
Yeah, cross validation.
Yeah, the cross-validation, because that's what you use. Cross-validation is what you use to test hyperparameters, right? You set a value of a hyperparameter, then you do the cross-validation with the, you do the k-fold cross-validation. And don't worry if you don't understand this term, because they go through it in quite a lot of detail later on. So k-fold validation is, yeah.
So one thing that was brought up in the text that we just read was that the cross-validation has the cost of like more training time.
Yes.
Is that right?
Yes.
Yeah.
Yeah, because let's look at it this way. See, normally they say 5-fold or 10-fold cross-validation. That means you divide the data set into 10 pieces, into 10 segments, each of equal length, right? And then you take, say if you're doing 10-fold cross-validation, you take 9 of the segments and build a model based on that data, and then you try to predict on the 10th piece of data, on the 10th segment, right? Then you take a different 9 sets of data and predict on the 10th, and you get to do this 10 times. You get to have, there are 10 different sets of 9 that you can use to build model with, and then you can predict on the 10th piece. Does that make sense? So you get to average together 10 models, and so that you get a really nice accurate measure of how accurate it is, because you're averaging together stuff, right? Averaging usually gives you an advantage. But the cost is that you now have to evaluate this thing 10 times. You have to evaluate this thing 10 times on each of your sets of 9, right? Yeah. So that's an overhead cost. Whereas if you just did, say 3-fold validation, then you divide the data into 3 equal pieces, and then you only have to do it 3 times. So there's a trade-off. The time, the time it takes you to do to run the model, that's one thing. And on the other hand is the accuracy that you get out of it. The more folds in your cross-validation, the better, the more averaging you get to do, and the better your accuracy will be. But at the cost of evaluating the model many more times. And the extreme version is, let's suppose you had 100 data points, right? You can do what they call leave one out cross-validations. That means you make 99 different data sets where you only have one, you have 99 points and you predict only on the remaining point, right? You can do that 99 different ways. So you get to average together 100 different models and make that prediction. So you get a really accurate prediction, but the cost is you have to run the model 100 times, and that can be expensive computationally. So you've really put your finger on an interesting point there.
I guess to extend on that, my question is like to kind of like, what are the heuristics? I mean, to decide on when to use cross-validation. I mean, if suppose my data is mostly pretty homogeneous, and then I don't know how much help a cross-validation can give me, instead of like, suppose I'm expecting to see completely a different kind of samples in the field.
Yeah, I mean, if your data is changing so much, I think they call it domain drift or something. If your real-time examples when you go to inference are going to be way different from the examples you have had, that your limited version, your limited set of training data, there's really not much you can do about the poorness of the generalization, right? It's,
yeah.
If the test data is significantly different, distributed differently than the training data or the validation data, you're not going to be able to do a good job predicting it on it. Yeah.
Joseph?
Yes.
I'm pretty sure you like cross-validation is pretty, you're leaving out a validation set. And if you check the scikit-learn link that I posted in the chat, that's what it talks about. And pretty much a lot of times you need to do cross-validation.
I think that's what I said, right? I mean, you build, for example, if you have fivefold cross-validation, then you divide your data into 5 equal segments, and then you hold out one of those segments, and you use the other 4 segments to build a model and predict on the held out segment.
Right.
And
So
there's 5 different ways you can do that, and so you get to build 5 different models and average them together, and that gives you a very good estimate of your generalization error.
Right. So in that way, you don't have to leave out a validation set anymore because you're already doing it by doing cross-validation.
Oh, you mean just you don't really need, you just use it on the training. You just use it on the training data. You don't really need a validation set.
That's right.
I see. Yes, that can be true if you already know which model you're going to use. But well, I guess you can use cross-validation to do model selection too. So I think you have a point. I mean, if you're going to just have one held out test set and then all the other data gets used to build a model and test it, build different models and try different values of hyperparameters and pick the best model, I think that I'll have to think more about that. Yeah.
Research, that's what
Yes.
it is.
Yes.
Scikit-learn, you can put in the hyperparameters or
yeah.
and grid search it.
Exactly. So like if you have a regularization parameter, you can give scikit-learn a range that you want it to test, and then a grid, a grid of values. I want it to test, everything between 0 and 3 in increments of 0.5 or something like that, and then it will make a grid of different values and run it once with each value and give you which value gave you the best. You can make a plot. This value, accuracy versus hyperparameter value, and then you choose the value that gives you the best accuracy. Yeah. Right. So this is kind of a different. So Wenching is pointing to a different paradigm where you don't really have a separate validation set. You just have one training set, and you use it, but you use it to do cross-validation. But implicitly, you are using the held out set as the validation set, right? So if you take if you take the training set and divide and do the do 5-fold cross-validation, right? You have 1/5 of your data that's being held out as a validation set. So implicitly, you're already doing that validation set. It's just a different way of looking at it. Does that make sense, Wenching?
Yes. So in scikit-learn documentation I posted, you also it's beneficial when you have not much data to be leaving out 1/3 of the data.
Yeah, because averaging always helps like that. Yeah, but then the trade-off is how much, if you leave out 1/10 of your data, then you have to run 10 models. If you leave out 1/3 of your data, you only have to run 3 models. So there's a trade-off between how much benefit do you want to get from averaging. You want how accurately do you want to predict your generalization error, and do you have enough time, computer time, to do it? So if you want to get the best prediction, you try maybe 100-fold cross-validation, right? Or but that means you have to run 100 models, and it takes time. But the trade-off is you get a better accuracy. So it's always, people generally just don't even think about it, and they just use 5-fold cross-validation. But as Wenching pointing to a very nice resource, the scikit-learn has a really excellent documentation. You can learn a lot by just browsing among the, if you browse among the documentation, if you're trying to figure out something, like suppose you're interested in gradient boosting machines and models, you can look that up in their documentation, and they give you a nice introduction to it. It's kind of like Stack Overflow in that sense, that you get a lot of information. Okay, any other questions? I think we've actually probed a lot of those 19 questions at the end of the chapter. Does anybody have any of those that they really want to hear discussed, of the 19 exercises? Does everybody know the difference between a model parameter and a hyperparameter? Does somebody want to explain that?
Yes, this is Shubhashish. So the model the difference, there is a very good illustration that was given there. Let's say we have created one model which is a very linear, simple linear regression model, theta 0 plus theta 1x. So in that case, first when we want to decide on the parameters, so firstly this theta 0 and theta 1, these are the model parameters. So depending on this one, if we vary theta 0, in that case the model is going up or down. That is the 1 degree of freedom. Second degree of freedom is theta 1, which decides how much slanting or how much slope the model is having. So these, by changing these parameters, we are actually changing the parameter shape, a model shape. So this is the model parameter.
Yes.
Now, once we decide on this model parameter, after that, when we don't want to overfit on a particular data on this, let's say on this theta 0 plus theta 1x model, we don't want to overfit. So in that case, what we do is that we apply some regularization, so that is this regularization parameter which makes sure that it is not overfitting this particular data set that we have.
Yes.
So that may understand the difference.
Yeah, and that's an excellent example. In general, a model parameter is something that that gets automatically fitted in your model. It gets calculated in your model. So in the example that Subhashish was talking about, you're trying to fit data to a line. So the two parameters of a line are the slope and the intercept, and the model will fit those parameters automatically. But the difference, so those are model parameters. They get automatically fitted by your model. But a hyperparameter is set outside your model. So if you want to, as Subhashish said, if you want to apply regularization, you have to decide like what should be the regularization parameter. And you set that regularization parameter. Should it be 3 or should it be 0.1? You make that decision outside the model, so it is not fitted in the model. So that's the difference between a hyperparameter and a model parameter.
Joseph, I've got a question regarding this one. So for this regularization parameter, isn't there any automated way to decide that? Do we need to manually test, like go through trial and error with all the parameters?
That's a really good question. And that's what Wenqing was talking about. He said that he told us that in scikit-learn, you have this grid search feature, a grid search feature that allows you to automatically crank through a bunch of different values that you can specify, and then you can figure out which the best one was. Yeah.
Okay, thanks.
Really good question. Any of those other 19 questions? Machine learning. Problems. So this one, number 2, it says 4 types of problems where machine learning shines. And it's interesting because on pages 5 and 6 and 7, I think he lists about a dozen of them. So it's nice to just sort of see that as a broader overview. These are the kind of problems that machine learning practitioners, machine learning and deep learning practitioners spend sometimes their whole careers doing. So if you look on pages 5 and 6, there image classification, there's semantic segmentation. That means semantic means meaning. So semantic segmentation applied to imaging would mean like dividing the image into different objects. For example, in automated driving, for example, you want to know whether something is a pedestrian or whether it's another car or whether it's the street or whether it's a fire hydrant, right? That's image segmentation. And then there's automatically classifying news articles. That's a natural language processing task. There's a lot of natural language processing tasks like summarizing text, question answering, speech recognition. So those are problems under the natural language processing. But then there's also regression, where you have features which are basically numbers, and you want to predict something which is also a number. So they sometimes will call that a target. So you want to, the input is just a bunch of numbers, and you want to predict the target, which could be like commonly like the sales. How many widgets are you going to sell? How much money are you going to make next year? That would be like a regression problem. Or how much should this house be worth if I tell you what its features are, like if it's a 2-bedroom house, or how many bathrooms it has, how many square feet it has, what zip code it's located in. You give me all those features, and then I build a model, and I'll predict what the price is. That's a regression model where you're trying to predict a numerical value. A classification problem is where you're trying to predict a class. For example, if you're given a bunch of images and you want to predict whether it's a bird or a dog or a cow, you know, there's different classes, different kinds of animals. So there are a finite number of classes, and you're trying to predict which class that is. So these are all the interesting kind of problems that occur in machine learning. So that's that problem. Any other ones you'd like to focus on of these 19 questions? Okay, I think that you as a community have done a great job of probing, of asking good questions, and we've actually covered a lot of the material among those 19 questions. So I think we've done a good job tonight. Thank you all for being here, and we'll close up and we'll meet again on